type of bond that we must go and have a look at is the ionic bond. Just want to see something before I get there. Okay. Yeah, I've got another note for you because we need to know about the forces between particles. It's just they've written it just to make it look like the others. Verstaan jy? But it's not. Technically, we write it H2O. But it's not wrong. I think they've just done it because it fits into the pattern of the other non-metal hydrides. Okay. All right. I've handed out a note, and it's got to do with the forces between particles. Now, I haven't done ionic bonding in detail. We don't do much more in terms of ionic bonding than what we've had. For example, if I want to look at the bonding between sodium and chlorine to form sodium chloride, then I have one sodium atom with one electron in its outer shell. All right, and I have one chlorine atom with 7 electrons in its outer shell, 4, 5, 6, 7, and we find that the sodium, because it is the metal, is going to give its electron to chlorine, and we are going to get a positive ion and a negative ion. What force lies there between positive and negative ions? Coulomb or electrostatic forces. And from what we've done previously, we consider these forces to be, relatively speaking, strong. If I had a look at something like magnesium oxide, all right, then I will have MgO. I will have a magnesium atom, and I will have an oxygen atom. Oxygen has 6 electrons. Magnesium has 2. And we are going to find that the magnesium is going to give its electrons to the chlorine, the oxygen, sorry. And we are going to get +2, -2. That's exactly what I want to show you now. What forces are between the magnesium and the oxygen ions? Electrostatic forces. But can you see that the charge is bigger? If you had to say which one has the higher boiling point? Magnesium oxide. It's got stronger forces holding the particles together. Do you understand? There's another factor that will influence the force between the particles. Sodium and chlorine they all lie in group 1, 2, 3. The third period, and oxygen lies in the second period. What will make the forces even stronger, because oxygen lies in the second period, it's got one shell less. So the particles can get closer together. So the forces act over a shorter distance. It's like having 2 magnets. If they're far away, the force is weak. But if I get them close, the force is strong. And that also contributes to this one having a higher melting and boiling point. No, both will be higher, because the forces that have to be overcome is greater. Okay. Do you understand this? Okay. Now, in the notes that I've handed out, there we're going to have a look at the forces between particles. Now, when I talk about particles, they can be atoms, they can be ions, and they can be molecules. Why are metals strong? Positive atomic rests in a sea of delocalized electrons. What type of forces hold them together? Electrostatic, Coulomb forces. Do you understand? All right. No, ions. There are ions in metallic bonds, yes. because the positive atomic rests have lost their outer shell electrons. They are delocalized. So we have resulting ions. Technically, metals are crystalline, and the particles are ions and electrons. Positive ions and electrons. All right. Okay. Now, in the note that I've given you, the first one is forces between ions. That is usually the easiest to understand. Because we have charged particles, the forces that hold these particles together are strong Coulomb forces. If the charge is bigger, like we've just seen in the example, the forces are stronger. Right. The problem comes in when we have, well, atoms and molecules especially. If I have water, oxygen and hydrogen, and I have another water molecule, and I have the hydrogens on it, and I have another water molecule with the corresponding hydrogens on them. What forces are there between these particles? When we did the characteristics of molecular substances, soft solids, low melting and boiling points, weak forces. Yes, the forces between molecules are weak, and the name of the forces are van der Waals forces. All right? It's the name of the forces. But it's never as very simple as that. Van der Waals forces actually incorporate a couple of things. All right? So if you're going to have a look at the diagrams that I've given you, there's an A and there's a B part. A, London or dispersion forces. Now, they are both intermolecular, between molecules. What does intramolecular mean? Inside. Intramolecular, what forces do I have? Covalent bonds. You understand? The forces holding the hydrogens and the oxygens are covalent bonds. All right? Intramolecular. But inter is between. The Inter-Cape bus goes between Cape Town and Windhoek. All right? So it's between. Intermolecular forces are these weak van der Waals forces. Now, the two that you must know of, they talk about London or dispersion forces. And the other one is so-called hydrogen bonds, but it's not a chemical bond. Yeah, just hang on. The hydrogen bond is not a chemical bond. It's an intermolecular force. All right? Now, if I have a molecule, let's say I have chlorine, it's a gas. Diatomic, so two chlorine atoms are covalently bonded. And they're giving me a chlorine molecule. Are you with me? Okay. I have lots of chlorine molecules. What forces do we get between them? Weak van der Waals forces. All right. Now, what happens is, when we talk about London or dispersion forces, remember these particles have energy and they bump into each other. Now, if this molecule would, for example, bump into that one, for the split second that they make contact, the electrons are able to be pushed away from each other. And they will push the electrons of the one to the other side, and we say just for a moment, it makes the molecule slightly polar. All right. So the force at that point of contact is an induced dipole. All right. It wasn't a polar molecule, but just when they connected, because the electrons can be pushed around, we get a slight positive and a slight negative side to the molecule. And when we have a slight positive and a negative side, it's a dipole. So this is an induced dipole. Now, this type of forces are known as London or dispersion forces. You don't have to remember about the induced dipole. I just used to explain it. Okay? So between my molecular substances, diatomic molecules, most of them are gases. Bromine's a liquid, iodine's a solid, but it easily undergoes sublimation. So are the forces strong holding them together? No. What forces do we have between those molecules? We have London or dispersion forces. They are weak. Then we get special van der Waals forces, and that is what we get between water molecules. If I go back to my water molecules, remember we said the water molecules have a slight negative charge, all right, there, and a slight positive charge. So, negative and positive will attract. Okay? And these forces are definitely going to be stronger than what they would be between two consecutive, no, I must go the other way, iodine molecules. Do you understand? Because the iodine molecule, it doesn't have a slight positive or a slight negative side. Now, those forces between water molecules that arise as a result of the polarity of the water molecule, we call those forces hydrogen bonds. But technically they are not chemical bonds. But this is why water that is a polar liquid tends to have higher melting and boiling points than other molecular liquids. All right. Actually, most of the other molecular substances are gases. Carbon dioxide, sulfur dioxide, hydrogen sulfide. If you can think of a molecular gas or a molecular substance, it is in the form of a gas. Why? Because the forces between the particles are very weak. There are a couple of exceptions. One of them is water. Now, when do we get hydrogen bonds? Usually, when hydrogen bonds onto oxygen, nitrogen, or fluorine. There is another added factor. The molecule mustn't be symmetrical. Because if it's symmetrical, then the charge distribution is equal. All right, and we don't have the resulting polarity. So, yes, ammonium, but ammonia will be slightly polar. All right. Do you follow? So when do we get hydrogen bonds between molecules? Usually molecules made up when hydrogen bonds onto oxygen, hydrogen bonds onto nitrogen, and hydrogen bonds onto fluorine. Now, we don't really work with the hydrogen nitrides. It's a chemistry that sort of goes on its own. But hydrogen fluoride, we can work with that one. And hydrogen fluoride will probably be polar. Why? Because we have hydrogen and we have fluorine sharing electrons, but fluorine has a very strong force of attraction on the electron pair that they share. Now, no, one bonding place, one bonding place, okay? We refer to the electronegativity of an element. Electronegativity is an indication of the attractive force on a shared pair of electrons. And when you look at the periodic table, fluorine is the most electronegative element. So electronegativities increase from left to right and decrease from top to bottom. So, when hydrogen bonds onto nitrogen, oxygen, fluorine, they are of the most electronegative elements. We find that are the electrons shared equally? Nope. They all attract the electrons away from hydrogen, making the molecule slightly more negative and slightly more positive. In water, it's very extreme because of the lone pairs and the angular shape of water. All right. So hydrogen bonds are stronger intermolecular forces. So if you look at the notes, I try to show it with diagrams. London or dispersion forces, they lie between molecules, and the forces are, relatively speaking, weak. We call them London or dispersion forces. You don't need, yes, they are collectively van der Waals forces. But if they want to go, if they ask you what's the difference between, why does water have a higher boiling point than hydrogen chloride? Then you have to go and explain about the forces. All right. Hydrogen bonds, special van der Waals forces. The hydrogen bond lies between molecules. Strictly speaking, it is not a chemical bond. Okay. That about the forces between particles. Now, ionic bonds, there's not much I want to say there. People, you should be able to do the ionic bonds of the first 20 elements, metals with non-metals. That hasn't changed. Nothing has changed from what you've done it from grade 8. Okay? If you don't understand it, you must go and try and do them, and then you must come to me and you must ask. Okay? But you should be able to do the ionic bonding. It's not difficult. Then there in your books on page 32, table 2.14, properties of ionic and covalent compounds. The ionic compounds, they say, are crystalline solids. Crystals are hard, brittle solids. The second point, when they are melted or dissolved, you can write in, they will conduct electricity. They have high melting points, high boiling points. They have high heats of fusion and vaporization. Janus, why? I suggest you come and sit on the side of the pillar. Jy gaan breinskade opdoen, regtig. Nee, jy sit en kyk in haar oë. Jy doen. Want jy sit en praat. Gaan sit daar, want jy kan nie my vraag antwoord nie. Move. Ek gaan nou kyk. Skuif, broer. Waar is jou boeke? Ek kyk dat jy dit inskryf, maar hy het dit nie ingeskryf nie. Seriously? Oh, how depressing. Hy moet pas op, hy sal dalk nie vir sy vrou eendag kan sorg nie. Okay, people, we said the ionic solids, hard brittle solids, high melting and boiling points, all right? They have high heats of, latent heats of fusion and latent heats of vaporization. What's that? Fusion is melting. It's the energy needed to separate the particles so that they can melt, so that they can slide over one another. And vaporization is the energy needed to overcome the attractive forces so that the particles can move freely as a gas. It connects up with high melting and boiling points. All right. Then the covalent compounds, most of them are liquids or gases. If they are solids, like iodine, they usually undergo sublimation. Who knows what mothballs are? What type of bond would be between those particles? Or what force holds the particles together is probably a better word. Weak van der Waals forces, they undergo sublimation. Those air fresheners that they put in the toilets, the little block in the cellophane paper, it's going to be molecular because it undergoes sublimation. There's usually an exception or so, but I don't know of an exception. All right. Yes, the naphthalene is bonded covalently. The forces between the molecules are weak van der Waals forces. That is why they can undergo sublimation. And then one difference then with the molecular compounds, they do not have an ionic charge. If there is no charge, can they conduct electricity? No, because current is moving charge. No charges that can move, then it cannot conduct in any state. Why can't salts conduct in the solid state? Sodium chloride salt, it doesn't conduct electricity when it's solid. Why not? In other words, the particles are held in a fixed position. Can they move? Only the vibration, according to the theory, but they can't move. And for you to be able to, or a substance to be able to conduct electricity, there must be charges that can move. But when it's liquid, the attractive forces have partially been overcome. Now the ions can slide over one another. You with me?
Now, can you ever get a pure liquid of salt?
A liquid of salt, yes.
Pure.
Yes.
Simply no water.
Yes. They just have very high melting and boiling points. For example, aluminium oxide, I think the melting point is something like 1,500 degrees or something like that. Okay. That is why they use salt in these new type of salt generators. It's the one that they have near Uppington. It is, I think there's salt in it, and it from the sun, yes. And the salt has a very high melting point, so when the salt becomes molten, there's lots of energy in it, and it can give this heat to boil water, which makes steam, which drives a turbine, which generates electricity. Yeah, just more or less. Yeah. Yes. Yes, you can burn because it will be extremely hot. All right. You could go to them. If they had to work on them, they would go at night. Or they would disable the mirrors. But it's probably just easier to go at night. Okay. All right. Ionic crystals, they're on page 33. Just know very strong what forces hold them together, Coulomb forces. The orderly arrangement is a crystal lattice. Okay, and now one of those strange things in your syllabus, we don't go into the shapes of the crystals. That becomes a separate part in chemistry. You can recognize which substance you have on the shape of the crystals that have been formed. So crystalline shape is unique for different substances. Now, in sodium chloride, they specifically want you to know the arrangement of the particles in the sodium chloride crystal lattice. We say sodium chloride forms a cubic structure, close-packed cubic structure. In each sodium chloride crystal, the pattern that is repeated is one sodium ion is surrounded in 3 dimensions, so in the front, in the back, to the left, to the right, to the top, to the bottom, by 6 chloride ions. And each chloride ion is surrounded in 3 dimensions with 6 sodium ions to form this cubic structure of the crystal lattice. Yes, that part there. That is the only one you need to know of. They have asked this in the external exam. I don't know why they go and just refer to one particular crystal and its shape. I think maybe just to sort of give you the notice that they do have unique shapes and arrangements to their lattice. All right. So please take note, sodium chloride with the arrangement of 6 sodium ions surrounded by, or surrounding each chloride ion, and around each sodium we have 6 chlorides in 3 dimensions. It's impossible to draw because I can't go in front and back. But you can, if you go on YouTube, you will find sometimes the molecular shapes that they build with models, and you can get that. When I break a sodium chloride crystal, it will break along a specific plane. And that is why it will always, whether I have a big block of salt like this in its crystalline structure, or I have a little grain of salt that I can put over my food. If you looked at it under a microscope, it would have the same shape, the crystal. Okay. Yes, yes, it goes along a face. All right.
So that is why when you cut it at the ends at that point, it kind of, you can chop it only in the middle and it will
Yeah.
end up split.
Yeah. If I have, well, water, I've got H2O. I know specifically I have 3 atoms, 2 hydrogens and 1 oxygen. But if I have sodium chloride, how many do I have? In a crystal lattice, there can be billions. And in a smaller one, there can be millions. And in an even smaller one, there will be thousands. Do you understand? The formula just gives me the ratio in which they occur. It doesn't give me the number of ions that I have in the salt that I shake. If I could pick up a little crystal, there's not only 2 ions in that one. There are millions. Okay. So that is another thing with the formula of salts. It just gives me the ratio in which the elements occur to each other. It does not give you, like in a molecule, I've got exactly 2 hydrogens and 1 oxygen. It can vary in my salts. Okay. If I have a tiny little crystal, I'll have less ions than if I had a big block of crystal. Okay. That is there on page 33. And then they've got electronegativity. They say it is the name given to the tendency of elements. It's actually the nucleus of an element to attract electrons. Elements such as sodium have low electronegativities. What does that mean if something has a low electronegativity? Does it have a strong force of attraction on its electrons? No. What type of ions do metals form? Positive or negative? Why? Because they lose electrons. Why do they lose electrons? They have low electronegativities. Non-metals have higher electronegativities. That's why they gain them. Do you understand? If you want to go technically into bonding, then we get sharing of electrons when the electronegativity difference lies between 2 parameters. And if the electronegativity goes beyond those 2 the difference, then we get a loss and a gain of electrons. That's when we get the ionic bond. All right, because they don't share them equally. The one takes it away from the other because it's got a higher electronegativity. Okay, yeah, they are. All right. The electronegativity on the periodic table, just very simply, if you remember fluorine is the most electronegative element, then the electronegativity becomes less from left to right, and it will decrease from top to bottom. What? There's nothing to explain. I said to you, fluorine is the most electronegative. So electronegativity increases. Oh, I've did it to decrease. Okay. I'm with you now. Okay. No. Still the wrong way around. Seriously? There, I want to do that. Okay, Josh, Darsel, right, because fluorine is the most electronegative. It's some of the stupid stuff that person remembers. It's got a value of 4. All right. The other elements are all less electronegative. Oh, this one is also the wrong way around. Seriously. Yeah, must go like that. Yes, it decreases. Bigger than and smaller than. Okay. This is bigger than. The metals have low electronegativity, and it decreases as you go down, because as we go down, then the electronegativity difference will also decrease. Sal ons nog aangaan? Okay, one more thing. The coordinate bond. a coordinate bond, we said both the shared electrons come from one partner only. And one example was ammonia. Okay, there and there and there and there. So this is NH3.